Hello. For the last conceptual lecture in this unit, I'm going to talk a little bit about more abstract or symbolic algebra that we can do with matrices and vectors and so on. With scalars, we can manipulate algebraic expressions to do lots of interesting things, right? So we can do things like apply the distributive principle to the sum of two scalars, xa plus x plus a times x plus b, and get x squared plus a plus bx plus ab. We can go in the reverse direction, and we can do something like take a quadratic expression and complete the square, rewriting x squared plus 6x plus 8 to x squared plus 6x plus 9 minus 1, and then recognize that this is x plus 3 squared, and so on. And in order to do these sorts of manipulations, we need to just understand the rules of how we work with addition and multiplication of scalars. We can do the same thing with expressions of matrices, with symbolic expressions, algebraic expressions of matrices, but in order to do so, we need to understand the rules. These manipulations can be helpful in transforming a problem that we might not initially know how to solve as it's given into a form where we can use tools that we do know how to work with. And we'll see multiple examples of this as we go through the semester. This sort of symbolic matrix algebra is not really the major core part of the course. We're not going to really be doing a tremendous amount with this, but we do really need to know the fundamentals of how we work symbolically with matrices in order to understand the solutions to various problems through the semester. So let me sort of just summarize what the rules are. Most of them are quite straightforward, and they follow from the definitions. Right? Matrix addition. Matrix addition, we're just adding corresponding scalars, the elements and the scalar elements, and so we would think that the rules of matrix addition should really follow all of the same rules of scalar addition. And it does. Matrix addition is what we call associative and commutative. That is, the order doesn't matter. We can add B and C and then add A, or add and B and then add C, and we get the same answer. A plus B and B plus A mean exactly the same thing, give us exactly the same thing. Matrix multiplication, however, is usually not commutative. Multiplying matrices, remember, takes these dot products of rows and columns. If we change the order, well then we're working with the rows of one matrix instead of the columns, and the columns of the other instead of the rows. And so this is generally not true. A times B is usually not equal to B times A. In many cases, A times B isn't even the same size of B times A, and even if they are, they're usually not the same. However, matrix multiplication is associative. If we take a B times C and then we multiply it by A with putting A on the left, that's the same as multiplying A times B and then multiplying by C with C on the right. Right? This means that we can just write a product ABC without using parentheses, and it's well defined. Matrix multiplication and addition are distributive with respect to one another. What does that mean? It means that A times B plus C is A times B plus A times C. And A plus B times C is A times C plus B times C. All right? So far, the only place where things are different than scalars is in this very, very important point of the lack of commutativity of matrix multiplication. Right. Scalar multiplication is associative and commutative. Remember, scalar multiplication, we're just multiplying all of the elements by the same scalar. Makes sense that that would obey all of the same rules as multiplication of scalars. K times A plus B is Ka plus Kb. K plus L times A, where K and L are both scalars, is K times A plus L times A. It doesn't matter if we write K times A or A times K, they mean the same thing. Right? The order, sort of furthermore, doesn't matter that we can put a constant into a product. K times the product AB, we could multiply A by K and then by B. We can multiply K by B and then by A, from the right order, and so on. It doesn't matter kind of which one we do it, right? Of course, all of these rules assume that the dimensions match in the right way, right? The rules only hold when the expression makes sense for the size of the matrices. Because we can treat vectors either as column vectors or row vectors, once we make a sort of a common definition, we're going to say, okay, I'm going to treat all vectors as column vectors as our standard. We can treat them exactly the same way, and all of the same rules apply. We don't need a different set of rules for vectors. We just treat vectors as if they were single row or single column matrices and use the rules for matrices. There were a couple other operations that we defined. We defined the transpose. The transpose of a matrix can be distributed into matrix addition and into matrix multiplication, but for matrix multiplication we have a really interesting thing. For addition, the transpose of A plus B is just the transpose of A plus the transpose of B. We also know that for addition the order doesn't matter, so we could move that around. For matrix multiplication, the order does matter. Right? And the order changes when we distribute the transpose. The transpose of A times B is B transpose times A transpose. We have to switch this for a very, very important reason. Imagine that I had some 2 by 3 matrix, and I multiplied that by a 3 by 1 matrix. This would give us a 3 by 1. If I just try to take the transpose of A, well, that's 3 by 2. And if I just take the transpose of B, that's 1 by 3. This expression doesn't have a match of the inner dimensions, unlike the original product did. And so we can't do anything with this. But if we switch the order, if we take this and move it over to the other side, then we have a 1 by 3 multiplied by a 3 by 2. Now the inner dimensions match again. We can do this multiplication, and the result is a 1 by 2. Sorry, I apologize, my very poor writing with a touchpad. This kind of just motivates why we need to do this. This doesn't actually demonstrate, prove that this must be true. We'll, for now, just take this as a given that we can distribute the transpose into matrix multiplication, but we have to switch the order. A very similar rule occurs with matrix multiplication in the inverse. The inverse of a matrix can be distributed into matrix multiplication as long as this inverse exists, right? If A, B has an inverse, then and A and B have inverses, which is true, right? If A and B inverse, and actually A and B have to have inverses and vice versa. If the inverse for AB exists, then it will be equal to the inverse of B times the inverse of A, where we distribute the inverse and change the order. Right? Again, this order change is essential. The inverse does not distribute into matrix addition. A plus B inverse does not equal A inverse plus B inverse. And in general, there is no relationship between whether the inverse of A plus B exists and whether the inverse of A and inverse of B exists. These are issues we'll get into more once we start talking about matrix inverses, but I wanted to present these here so the rules of how we do symbolic matrix algebra are all sitting in one place. Right? We've talked also about zero and the identity. We also can take advantage of these in simplifying expressions. We can add a zero matrix of the right size to any matrix and it doesn't change it. We can multiply the identity of the right size by any matrix and it doesn't change it. This can go in kind of both directions. We can add in an addition of a zero anytime we want. We can add in a multiplication by the identity anytime we want. We can also remove zeros and remove identities to simplify expressions as needs be. Also, 0 times a matrix is 0. Again, however, very important to remember that this 0 and this 0 might not be of the same size. You may sometimes encounter a ones matrix, a matrix kind of defined similarly as the zeros matrix, but having ones everywhere. There's plenty of uses for a ones matrix in terms of expressing certain kinds of relationships and so on. The ones matrix does not really have any special algebraic rules. It is not the identity. The ones matrix times A is not A. A times the ones matrix is not A, and they're not equal to each other. The ones matrix has a place in defining certain kinds of linear algebraic mathematical models and to mean certain things in model construction. it doesn't have any sort of special meaning when we're working sort of symbolically with symbolic algebra. All right. That wraps up our sort of discussion of the rules of matrix algebra. They give us everything we need to do symbolic manipulations. A lot of it is similar to what we do for algebra with scalars, but there are some important subtle differences, especially in the commutativity of matrix multiplication and in the sort of reversal of order when we distribute inverses and transposes. These are things that you just get used to with practice. For the time being, just sort of keep these rules sort of deeply in mind. And we'll have some practice both in some worked examples that we'll go through in an accompanying video, as well as homework. That wraps up this unit. Take a look at the accompanying worked problems. They should be very informative in expanding some of the conceptual ideas that we have discussed so far. Thank you and goodbye.